Okay, so this lesson is going to be broken up into two videos. This first one is going to introduce piecewise defined functions. The second video will focus on creating the function and graphing it. So the first one, if we're going to talk about a piecewise defined function, we just want to define the term function, make sure we remember what that means. So when we're talking about a function, right, here off to the left it's been defined as a relation that maps a set of inputs, so values you could put into this function, to a set of outputs. And remember, every input can only have one output. So if we were talking about a graph and we were talking about a function, then we just remember it has to pass the vertical line test. So if we have any sort of graph on here or a function, let's say we're looking at an absolute value one, similar to the one we looked at, notice that if I were to draw vertical lines, it only touches the function once. Every vertical line I draw touches the function once. That would pass the vertical line test. Remember, if you have one that looks like this, so you have maybe a circle, this no longer passes that vertical line test because when I draw a vertical line, it actually touches the function twice. So one input, this input of x, would give me two different outputs. Okay, so it must pass the vertical line test. And then if we write them as an equation, we can replace the variable and we can evaluate a function, right? So for an example off to the right here, we have f of x is equal to 2x plus 5. This is a function, and we can evaluate it for different values. So if we evaluate f of negative 2, we're saying what is f when our x value is negative 2. So we come over here and we say, well, f of negative 2, using that function notation, would just be us using this function where we're inputting a negative 2. Then evaluating means we simplify as far as we can go. So 2 times negative 2 is negative 4, plus 5 there on the end. Negative 4 plus 5 would give us a value of 1. So at f of negative 2, we get the value 1. Functions can be represented in various ways, such as words, right? Tables, equations, or graphs. So we're going to review how to use a function given as an equation or a graph and evaluating to start with in this video. So this first example relates to an equation. I'm going to read through the example and then we'll answer the following questions. If a state has 6% sales tax, then we could use the function t of d is equal to 0.06d to calculate the amount of tax you would need to pay for any given purchase. In this case, t of d, okay, represents the total tax you're going to pay, and d represents the price of the item you want to purchase in dollars. Okay, it's very common when we create a function that we use variables that make sense. So they're saying this right here, right, represents the tax you're going to pay, and this d right here represents the dollars of the cost of this shirt. So we look down here, and part A says show how you would use the function to calculate the tax charged if you were to buy, misspelled there, so I replaced buy, a shirt for $25. So again, if my function is t of d is equal to 0.06d, and the shirt is going to be $25, 25 represents the d. So we would take this function and we would evaluate it at 25. We have 0.06, again putting 25 in for d. Now when you calculate that, 0.06 times 25, you're going to end up with 1.5. Now the question we always ask at the end of a word problem, or we feel like it's the end, is what was it asking me to find? What does this 1.5 mean? Well, this represents the amount of tax, right? So if you buy a $25 shirt, you're going to pay $1.50 for tax. Okay. Then if we look at B, again, use the function to calculate the tax charged if you were to buy a $20 shirt instead. So same function, we just are going to buy a different price shirt. So instead of putting 25 in, we're going to input 20. We like functions for this reason. We input a value, we get a value out. If we multiply 0.06 by 20, we end up with 1.2. So again, what does that mean? Well, that means that we're paying $1.20 in tax, right? Part C says, show how you would use the function to calculate the cost of the shirt in dollars that would require a payment of $192 in tax. Now, functions, right, we can go either direction with this. So again, I'm going to write out the function. We have T of D is equal to 0.06 times D. Now, in this case, you don't know the cost of the shirt, so I don't know what D is. So I'm going to have to solve for D, but I do know that the amount of tax is going to be $1.92. So we're going to say 192 is equal to 0.06 D, and we're solving for D because we're finding the dollars. So we divide by 0.06, and we end up getting D as equal to 32. Again, we ask, what does that mean? Well, that means that when we buy a $32 shirt, right, that is actually where we would pay that $1.92 in tax. So functions work going forwards, going backwards, inputs, outputs. One more question related to that. It says, how might the function be adjusted so that the function would give you the total purchase cost you would need to pay for the items purchased, not just the tax amount? So right now, you have the function. Again, I'm going to write it here. And when we calculate with this, it gives us the result there of just the amount of tax you're going to pay. Well, you're going to pay your tax on your shirt, but you also need to pay for the shirt, right? So we need to add the price of the shirt. Remember, D represents the price of the shirt. So if I make a new function, I'm going to give it a new name. So maybe this is the total cost. So I'm going to call it C of D. Okay. We're still going to pay tax, plus we need to pay for the shirt. And remember, D represented the shirt. So we can either write it that way, or those are like terms. So essentially, we could write it C of D is 1.06 D. Those would give us the same results there. Okay. So from an equation, we can input values and we can evaluate them and get output values. From a graph, let's look at a graph. So graphing a function is another way to view the relationship between two values, right? We can see a lot of the inputs are like our x values, the outputs are our y values, and every point on our graph represents an input and output. So we can evaluate the function on the graph by identifying which value corresponds to which value. So we've graphed a function f of t on this graph, and we're going to use it to find the indicated value. Now notice it passes the vertical line test. If I were to draw vertical lines on here, each one of those only touches the function once, so we're good. And it asks us to evaluate, first of all, f of 4. Now remember, this is the function f of t, so it's saying when t is equal to 4, so let me get a different color, right? When t is 4, what is the function value? So I come over here, and I come over on my t line until I find t is 4. And if you look up here, the function value is at 1. So that's like the 0.41. When t is 4, we're at 1. So our output here is going to be 1. Again, the second one says, well, what is f of 0? So again, we go to where t is, our t value is 0, which is right here. And when our time is 0, it looks like the function is at 1. So our output here is again a positive 1. Going the other direction, it says, what is the value of t? So now we're finding the value of t when the function is equal to 3. So this time it's the function output that's 3. So we're following our graph and we're figuring out, well, when does our graph hit 3? It looks like it hits 3 right here. So notice that the time at which it hits 3 is going to be 6. Okay, using that same idea on the next one, what is the value of t? Where f of t is -1, so I come over here, I look at my function, and it looks like it comes down here, right, and hits -1. And if we look at what t is, it looks like t is 2 when y is -1. Okay, so evaluating from a graph. And essentially this next example is kind of the same thing. So this says we place various amounts of information on a graph, right, to organize the information in a clear way. It's really easy to see from a graph instead of just looking at functions maybe or a bunch of points. So here's an example. Isaac lives 3 miles away from his school. School ended at 3 p.m., and Isaac begins his walk home with his friend Tate, who lives 1 mile away from the school in the direction of Isaac's house. Isaac stays at Tate's house for a little while and then heads towards home again. On the way, he made a stop at the library for a time. He then hurries home. The graph provided is a mapping of his walk home, comparing his distance from home and the time it took for him to make the journey home. So notice the two things being compared. We're going to call this time in hours, and it looks like it's distance in miles. So he's walking home, and we're comparing it to the time it takes him to get home. Use the graph to answer the following questions. So notice here's his trek home, right? This right here represents 3 o'clock. School's out, and he starts to walk home. So this would be like 4 o'clock. This would be 5 o'clock, right? These are hours that have passed. This would be 6 o'clock. So we're just looking at the time passing as we move this direction. And notice he's getting closer and closer to home. So school is 3 miles away. That's where he starts. He heads in the direction of home, but then he stays at his buddy's house for a little while, right? Then he starts walking home, and he goes to the library and gets distracted. And then he makes it all the way home. So he's changing his rate as we go. So when we look at that, part A says how much time has passed between school ending and Isaac getting home. So we're just looking at the total time, right? It looks like he was gone 1, 2, 3 hours, and then that point right there is labeled as 3.75. So, right, it took him 3 hours and 45 minutes to make it all the way home. Or you can put 3.75 hours. That's totally fine too. Okay. At what time did he make it home? So again, we just need to understand the context of the question. If this is 3 p.m. and it takes him another 3.75 hours to get home, that's going to be, right, 4 o'clock, 5 o'clock, 6 o'clock, and then 45 minutes. So he's going to get home at 6:45 p.m. Okay. And then again, if we're looking at what's happening here, right, this is when he's hanging out at his buddy's house. He's at Tate's house for a little while, so he didn't actually get closer to home. And then later he goes to the library, so I'm going to write that on there. C asks, how long did Isaac stay at Tate's house? Well, it looks like he got there right here, and then he left here. So we're going from here to here. There's 1 hour. There's 2 hours, so it looks like he stayed at his house for 2 hours. Okay. And we could continue answering these questions. They're just relating to this graph. I'm going to kind of jump ahead. But see if you can answer those last few questions. I'm going to jump to F. It says, how might we be able to represent Isaac's journey as a function? Now notice functions, right? This passes the vertical line test. But we also just have pieces of lines. So there's a piece, right? Here's a piece. Here's a piece. And every few hours, right, in the different time slots, we have a different function. So this one has a negative slope. This one has a 0 slope. This one has a negative slope. This one has a 0 slope. So we have different pieces there. This is what we call a piecewise function. And we have to be able to write the equations for each of these lines in and of themselves. But let's talk about evaluating first. So a piecewise function looks something like this that you see on the next page of your notes. And we name them using the function notation. So this one would be like f of x. This one is p of x. Notice they're both using an x input, but we distinguish them by naming them different value or variables there. So we've got f of x, and he looks like he's made up of 3 pieces, right? And p of x is made up of 2 different pieces. Notice this piece right here looks a little bit weird, right, after the comma. These are domain restrictions. Now again, if I were to go back to this graph with Isaac walking home, if this line kept going forever and it wasn't restricted, then it no longer passes that vertical line test. So in essence, we're only taking a piece of all of these lines. So when we get over here, this tells us which piece or where the piece is that we're taking, okay? So when you evaluate a function, just like we did on the front page, you just want to be aware of what the name of the function is that you're evaluating. So this is f of 1, meaning I'm going to choose the f function here, and then I'm going to evaluate it at 1. Now 1 doesn't exist in all of these pieces. It only exists in one of them, because to be a function, every input has a unique output. So f of 1, I look at the domains, and I am looking to see, is 1, if I were to put 1 in for x, is 1 less than negative 3? It's not, so it doesn't fit in there. Then I look at this next piece. Is 1 between the values negative 3 and 2? It is, right? So it works for this one. And we could check the third one. We could say, is 1 greater than or equal to 2? It's not. So essentially, we're going to use this equation to evaluate, sorry, that was crazy, this equation to evaluate at 1. So because it's just a 7, there's no variable parts. This guy's actually always 7. Okay, let's try it again. So going down, this is f. So I'm still using this left function, and we're going to evaluate it at 2. So again, we ask the question. We look at the domain. Is 2 less than negative 3? No. So this guy doesn't work for us. Is 2 between the values of negative 3 and 2? Now the value is 2, but notice it doesn't include 2 on that spot right there. But if we jump down to this domain, x is greater than or equal to 2. So 2 would fit into this piece right here. So we're going to take this equation and evaluate it. So we've got negative 1/2 plus 3, and again we're plugging in a positive 2. So we put the 2 in there. Then we just evaluate. So negative 1/2 times 2 is negative 1, plus that 3 would equal 2. And I'll box those so we can see them. All right, jumping down to the next one, this is a p function, so I'm going to use this function over here. P of negative 5. So again, we're going to look at negative 5 and see where it fits in. Is negative 5 less than negative 2? It is, right? Negative 5 is less than negative 2. So we're going to use this function to evaluate this piece. So we're going to go negative, right? Oops. We're using that piece, and we're inputting the negative 5. So we've got a negative, negative. That makes that a positive 5 minus 5, which is 0. Okay. Again, I'm just going to keep going. So moving to the right, again, we're back to the f function. So we're using the one on the left, and then we ask, where does negative 5 fit in? So we start at the top. Is negative 5 less than negative 3? Yes, it is. So we're going to use this function right here. We do 3, we put in negative 5, and we subtract 10. Then we evaluate negative 15 minus 10 is equal to negative 25. Okay. The next one, again, we're using the p function, and we're evaluating at 3. So we're going to use this one over here, and we ask, is 3 less than negative 2? It's not. Is 3 greater than or equal to negative 2? It is, right? So we're going to use this piece of the function. So we do 4 times, inputting that 3, is equal to 12. Okay. And then the last one, we've got f, so we're back to the f function and a positive 3. So again, we ask, is positive 3 less than negative 3? No. Is positive 3 between negative 3 and 2? No. Is positive 3 bigger than or equal to 2? Absolutely. So we're going to use this function. So we go negative 1/2, put in that 3, and then we have a plus 3. So negative 1/2, right? That's the same thing as negative 3/2 or negative 1.5. And if we add that together, that's actually 1.5. So you can put 1.5 or 3/2. Okay. So again, practicing identifying the name of the function, using that domain restriction to find the piece in which that value exists that you want to evaluate for, and then plug it into the correct piece and evaluate.